we'll talk about our experience with MIDAS Civil, some of projects that we have done in MIDAS, then modeling of steel tub girder bridge, then we'll talk about the load application, then design load rating procedure, and if we have some time, we'll also talk about load rating result verification that we did in this project. So we have been using this software for over 2 years now, and we have done multiple conduct projects in MIDAS Civil, and we have performed different very simple to complex bridges in MIDAS. Some of projects that we have done includes bridge design, load rating, and some of complex bridge analysis. It's also our go-to program for quick analysis. Some of our projects that we did in MIDAS includes steel plate girder bridge for construction stage analysis. We did a couple of load ratings such as steel vascular bridge, open spandrel, steel arch bridge. We also use this software for construction engineering such as stability checks for demolitions. This is one of our projects. It had over 93,000 elements and had 17 steps of construction. And we use this in this project. We did time-dependent construction stage analysis. This is steel vascular bridge, and we use MIDAS Civil for 3D modeling and load rating of this vascular bridge span. This is another project we did in MIDAS. It is open spandrel steel arch bridge. We use this project for 3D modeling of bridge, and we also use this software for independent load rating check. Okay, now I will talk about load rating of steel tub girder bridge. In this project, we have been asked to load rate composite girders, cross-member members in diaphragm, field splice, and decks. MIDAS Civil was used for load rating of composite girder, but MIDAS doesn't have a feature to load rate cross-frame and in diaphragm right now. So we use force and capacity evaluation for cross-frame members and stress evaluation for in diaphragm. These results were later used for load rating of cross-frame member and in diaphragm. Different spreadsheets were developed for load rating of deck and field splice. This is a general plan of simply supported curved steel tub girder bridge. It carries I-95 ramp over Lafayette Street in Bridgeport, Connecticut. Relatively, this bridge is small. Its span length is around 190 feet. This is a typical section of a bridge. Here we can see both internal and external cross-frame members, and deck has a super elevation. In our model, we haven't considered this super elevation, but we have considered other features like these varying hunch depth. This is a general framing plan. Here we can see lateral top flange bracing as well as internal and external cross-frame members. At both ends, we have in diaphragm. In this picture, in left-hand side picture, we can see a cross-frame inside a box girder, and right-hand side picture shows cross-frame members, external cross-frame members. In this, we can see internal cross-frame member inside a box girder, and this one is in diaphragm, external in diaphragm. Now let's talk about the modeling of a bridge. So I'll go back to my model. So once we create these nodes using MIDAS Civil, okay, this is a model that in which I will use to So in this model, we have three types of material that has been used. One is composite material. Composite material is defined for composite steel tub girder bridge. So in this section, we use SRC material as type of design, and we have to select required steel and concrete property, and MIDAS itself automatically generates material property as shown here. The other material that we need is steel material. We have used this material for cross frame and in diaphragm except steel girder, and we have selected the steel material that we need, and MIDAS automatically generates these material properties. Then there is one more material. I hope many MIDAS users already know about this. This is a dummy. This is for a dummy crossbeam element. This is actually material-wise. This is a concrete material, but this doesn't have any weight. To make sure like it doesn't have any weight, we have to change this weight density of concrete to 0. So we'll also talk about this in the later portion of our presentation. Sorry, webinar. Okay. So now we'll talk about our girders. So in this model, we have modeled this model with two different types of elements. One is beam elements, and one is plate elements. Plate elements were used to model in diaphragm, whereas other elements such as composite girder, crossbeam members were modeled using beam elements. This is an example of composite steel top girder bridge, section. In this dialog box, we can actually input slab dimensions such as thickness of slab, hunch dimension, and girder dimensions. Maybe I can change this to mm, it will be a lot easier. Okay. So this dialog box allows us to input girder and slab dimensions, and after doing this, we can get the required section. Regarding the material property of the composite section, we can go to select material dialog box from here and select the required material property. So, for example, for concrete, we can select our required material like this. It's very easy. Or if we have material information, we can manually input here. In our model, we also wanted to consider a creep effect. So we used multiple modulus of elasticity, and we have achieved that by changing this to 24. Initially it was 8, around 8. And in our model, anything concrete is weightless. And to achieve that in our composite girder sections, we have changed this ds to dc ratio to 0. By doing so, the concrete used in composite girder will become weightless. Okay. So let me show you our girders. So these two are our steel top girders. This one is girder 1 and this one is girder 2. Each girder has two different sections as shown in here. Okay, and right now we have two independent composite steel top girder sections as shown in this picture. They don't have any transverse continuity. So to maintain a transverse continuity of a deck, we need to model a dummy crossbeam element. Dummy crossbeam elements are modeled as a beam element, and these connects two girders and provides transverse continuity for the deck. The material used in this section is weightless concrete. Now let me take you back here. So for this element, the section property is similar as that of deck, and material-wise, it is our weightless concrete material. Okay. Now I'll show you how I model cross frame members. This is one typical cross-frame member that we have modeled in our model. To model this cross-frame member, we need secondary nodes. In my model, we have created this secondary node relative to primary node as shown in this picture. So once we create these nodes, we can connect with respective sections, and we will create cross-frame member as shown here. But right now, though we have this cross-frame member, this is not directly connected with our primary model. To connect with our primary model, we have used rigid elastic links as shown in this picture. So we have drawn a rigid elastic link that connects primary nodes with first, secondary node. Then we have a series of rigid elastic links that connects this whole node with our primary node. In this way, we have created our cross-frame member as well as connected this to our primary model. In our modeling of cross-frame member, we have used beam elements. Usually, these cross-frame members are modeled as truss element. Since we have used a beam element, we have to carry out beam in release, as shown in this picture. So I will take you back to my model and show you my cross-frame member and beam in release. Okay. So let me activate this. So this is my model right now. We have steel girder and we have cross-frame member inside it. Let me take one section. This. Okay, so I will activate some nodes. Okay, so this is our primary node as I've shown in previous picture, and we have created these nodes, secondary nodes, related to this primary node, and we created cross-frame element. If we take one example for cross-frame element, it's a basic section like T-section, T-sections or angles. We have selected the required section property, inbuilt section property, and we use that in this model. So once we create this model with required section, all we have to do is to connect these cross-frame member with our MIDAS model, primary MIDAS model, which is this girder element. So for that, we need an elastic link, which is this one. Then since this is a beam element, we also need to do beam in release. So we have done that. We have three types of beam in release for our cross-frame member. One is pin, and another is pin fixed, and the last one is fixed pin, or pin fixed, or fixed pin. Okay. So at this stage, we have created our composite girder. We have created our cross-frame members, and we have connected these cross-frame member with our model using rigid elastic links, and we also did in-beam release. So at this point, we have our girder and cross-frame members. Now let's talk about the modeling of in-diaphragm. In diaphragm. Off. Okay. So this is our in diaphragm. Maybe it will be a little easier if I show you my slides. So we have two in diaphragms, right? One is internal in diaphragm and one is external in diaphragm, as shown in these two pictures. These were modeled as plate elements and steel material was used. We have twin wave with stiffeners. Maybe you can see here, they have one. We have stiffener inside the box girder, and in diaphragms, top flange of diaphragm was composite with a deck, as shown in this picture. And creating this in diaphragm is a little bit complex because we have a very complex geometry. We have lots of nodes. To ease this process, we have to use an AutoCAD file. First, we create an AutoCAD file with one face of in diaphragm with openings and required plate elements. So once we create AutoCAD file, we save it as a DFX file, which we later can import in MIDAS Civil. And in our case, we have imported this DFX file and only taken these intersection point as our node. So with the help of DFX file, we got our first node for in diaphragms, which we later copied and moved to create other required nodes. Now let's and this is next slide. In this next slide, we can see how we connected our primary node with this in diaphragm. Right now, this once we model this in diaphragm, it's a separate model. It's not connected with our primary model. So we have to do that using. We have done that using elastic link. So our Girder node was considered a primary node, and nodes of in diaphragm were considered as secondary or slave nodes. So we connected these slave nodes with our primary node using rigid elastic links, as shown in this picture. At the end of this process, our model will look something like this. We have composite box girder, we have cross-frame members, and we have in diaphragm. So we'll go back to our model. So this is our in diaphragm, and I will show you our link. This is our link. So this node is actually a node of primary model, which is our steel top girder, and we have connected this with our in diaphragm node. I just removed one face of an in diaphragm, so we can see inside. Here we can see stiffeners inside a box girder, in diaphragm. This stiffener was modeled as a beam element. So we just selected solid rectangle and input required dimensions, and the material wise, this is a structural steel. So at the end of this step, we have box girder, we have cross-frame element, and we have in diaphragm. And we also model our dummy crossbeam element to have transverse continuity. Since we haven't assumed weight of concrete, we will apply weight of concrete separately. These are a few weights that we have applied in our model. One is self-weight of steel, which includes weight of steel top girder, cross-frame members, and in diaphragm. And we will also apply weight concrete load, as shown in this picture. We have also applied torque applied on a member model like this. We also applied a few other loads, such as load due to hunch, miscellaneous steel loads that we haven't considered in our model, additional concrete loads, SIP-form workload were also applied. All these loads were applied over our girder. After this, we'll talk about construction stage. So let me talk about the boundary condition first. We have unidirectional bearing support at one end, and we have fixed bearing support at the other end. And we model this using springs in our model. Construction, we have 4 construction stages. Construction stage 1 includes steel structure erection. Construction stage 2 includes weight concrete placement. Construction stage 3 includes composite action. In construction stage 4, we consider long-term effect. In construction stage 1, where we considered steel structure erection, we activated I hope some of our participants know how to use MIDAS, so maybe they are already familiar with this. So in construction stage 1, we activated steel top girder cross-frame elements in diaphragm, and boundary conditions such as support condition, elastic links, and beam in release. Load-wise, we activated self-weight of steel member and some miscellaneous steel weight. In construction stage 2, we activated weight concrete placement. So in this case, our deck is not composite. We haven't activated any new elements. We haven't activated any new boundary conditions. We only applied weight concrete loads. If you remember, that one is weight concrete UDL and weight concrete torque. In construction stage 3, we considered composite action. In this stage, we activated dummy cross beams, which provides transverse continuity. We have also activated relevant elastic links. We haven't activated any new loads in this stage. In construction stage 4, we have considered long-term effect on concrete property. In this stage, we haven't activated any new element. We only changed modular ratio. In boundary condition, we changed our modular ratio from 8 to 24, and parapet and wearing surface load were activated in this stage. Now we'll go back to our model. So for construction stage, as I have already told you, it's really easy to manage construction stage in MIDAS Civil. In construction stage, we have activated all the steel elements. If you want to activate any other elements, it's really easy. In MIDAS, we can just select the element and we can edit. So this is really easy. In construction stage 1, we activated all the steel elements. We have activated relevant boundary conditions, and some steel loads were also applied. Similarly, in construction stage 2, we activated weight concrete loads. We haven't activated any boundary condition, and we haven't activated any elements. Similarly, in construction stage 3, we have assumed in this stage we assumed composite action. So we also activated dummy cross beam elements, because now the deck is composite and we have that transverse action is there now. So we activated this dummy deck. We have also activated relevant rigid elastic links, and load-wise, we don't have any additional load. In construction stage 4, we activated parapet and wearing surface load. In boundary condition, we changed our modular ratio. So that's we have actually considering creep action in this stage. Element-wise, we don't have any new elements in this stage. We can this feature is very cool. We can see different construction stages. In construction stage 1, we have all our steel elements. In construction stage 2, we have only activated. We haven't activated any new elements, so we don't have anything here. But in construction stage 3, we have activated our composite action. So we have this dummy crossbeam element. In construction stage 4, we have considered creep action. So we don't have any new element, but concrete property had changed in this stage. Okay. So at this stage, we have created our model. We also have our construction stages. We also applied our different static loads. Now it's time for applying moving loads. Relatively, in my experience, applying moving load in MIDAS is easier. There are basic 3 steps to apply moving load in MIDAS Civil. One is defining a traffic lane. Second step is defining required vehicles. And third stage is defining a moving load case where we assign traffic lanes and vehicles. In this project, we had 15 trucks, 2 were design trucks, 2 were legal trucks, and we had like 11 permit trucks. These 4 are critical load placements that we considered in our load rating of steel top girder bridge. Each placements have 2 lanes as shown in these pictures. This is one of the example of legal or permit truck. This is Conneticut 204A. This is a non-standard design truck. So let's go back to our model. Okay. So we have 3 steps, right? Before that, going to those 3 steps, we have to select a moving load case. MIDAS Civil has variety of codes. In our case, ASTO LRFT is applicable, so we have selected this one. Let me activate all the girders. Activate. So these are 2 of our girders. And I'll also activate few nodes. Okay. So to define a moving load, first we have to define a traffic lane. So for each moving load case, we have 2 lanes as shown in this right and left hand side. So if you go to this dialog box, we can see 1 traffic lane. There are a variety of ways to apply traffic lane. In this model, I assign traffic lane relative to girder. So basically, we just give a eccentricity or relative location of traffic lane relative to a girder. In my case, it's like 126 mm. I will change this to feet. It will be easier to see them. Okay. So yeah. So by changing this eccentricity, we can define a relative location of lane relative to a girder. And this is a wheel spacing of our vehicle. If we have more than 1 girder, then in that case, for vehicular load distribution, we have to select crossbeam options. And for this purpose, we have a dummy crossbeam element, right? And in our case, it is deck dummy, which, if you remember, that's the element that we created, the dummy deck element that we created before. So we have this, and we have actually assigned. So this is our example of placement 1, live load placement 1. Here we have assigned lane load. We have defined traffic lane related to girder 1, and other traffic lane is defined relative to girder 2. So once we define this traffic lane, the next step is defining a vehicle. If we have to consider standard design trucks, MIDAS actually have standard trucks. Only we have to do is to select our code. For in this case is ASTO LRFT. Then MIDAS itself has a few options, that standard trucks option, and we can select any one of them. And it also has a place where we can input dynamic allowance factor. So this is for standard trucks. We don't have to change anything. But if we want to define a user-define a permit truck, so the permit truck, MIDAS doesn't have predefined permit trucks. In this case, we have to use user-defined vehicular load, and we come up with this dialog box where we can define any number of axle and any number of loads. For example, this is one of our permit truck. This is the spacing between 2 wheels, which is 11 feet, and the wheel load is 11. 11 keeps But in this dialog box, as you can see in this picture, we have to use only half of that, so it is 5.5. The distance between the length of the axle is 6 feet, so half is 3 feet. So we have like, this has like 6 axles as shown in this. So yeah. So at the end of this stage, we have defined traffic lane, and we also define our vehicles. The next stage is defining a moving load case, where we assign traffic lane and vehicles. So in this stage, if I go from here, in this stage, what we do is just select a vehicle, defined vehicle, and once we select this vehicle, we can add number of lanes that we need, or we want to apply vehicle on it. So we have, in this case, we have HL93 truck, and we are using placement. We are assuming placement 1, so we have these 2 lanes. For HL93 truck, we have assumed all 4 placement conditions. So for each placement conditions, we have 2 lanes. 2 lanes, and we are applying minimum 1 to maximum 1 lane loads. So at the end of this stage, we have defined traffic lane, moving load, and we have also created moving load case. So at the end of this stage, we can say like we have modeled a bridge. We have also created a construction stages. We have also applied moving loads. So now we'll talk about load rating, and we also talk about analysis and design features of MIDAS. Okay. So for that, we have this model. This is another model. This is the same model, but it has more elements. This is basically the same model that we use to load rate our bridge. Okay, so for this load rating purpose, we have few steps that we have to do. So I will go through each steps. First step is selecting a code. In our case, it's AstroRFT 2012, so we have selected this. Next stage is selecting a parameters. In this dialog box, either we can update by code or we can change as per our need. In this section, since we have 2 box girder, we have selected multiple box sections. Then we have to go to this dialog box, which is bridge rating group setting. In this setting, we can actually assign condition factor for each girder element. Since our girder is girder has condition factor 1, so all we have to do is to select girder and assign condition factor. For our case, it's 1. If in a single girder, if we have like some section are deteriorated and some are perfectly fine, in that case we may have multiple condition factor in the same girder. In that case, for each section of a girder, we can assign different condition factors from here. Next is rating material. Currently, for steel girder bridge, MIDAS does only load rating for composite materials. Sorry. So in this section, in material section, we have to assign a material which is SRC material, which is composite material, and we can also change material property at this location. So once we assign required material property, it's done. So next step after that will be defining a rating cases. Depending upon case project, we may have different cases. For example, we have like 15 trucks. So for each 15 trucks, we have rating cases. I will show you one. Sorry. For this case, we have assigned primary vehicle as HL93, and we have a rating factor here, which is 1.75. Similarly, we have other static loads, right? For example, DC before and after, that is before composite and after composite. We also have this temporary DW, which is wearing surface and parapet loads, and we can assign maximum and minimum rating factors. In this dialog box, we can select type of load from here, and we'll change our rating factor in this at this location. So for using this dialog box, we can come up with rating load combinations. Since once we have rating combinations, we have everything. But in this case, our bridge is curved, so we have to provide one additional information, which is curved bridge information. In our bridge, okay, I will open one simplified model. Maybe it will be okay. Okay, so in curved, if our bridge is straight, we don't have to worry about this section. But if the load rating of the bridge is curved, then in that case we have to select the girder. For example, in this case, let's go to a material. Active. Okay, so for example, if we want to assign a curved bridge information, we have to select a girder first. We'll select girder A, girder 1 in this case. Okay, so we have selected a girder information. We have selected a girder. Then we have to give a radius. In this case, it is 140 meter. So we can select we have to provide girder radius. Then type of curvature needs to be provided. For example, in our case, it's curved, so we just simply apply this. So this is one step that we have to consider if our bridge is curved. Else we can skip this step. Since we have already defined design code, we have already defined parameters, load rating cases. Now we can perform a load rating for composite girder. So let's perform a composite girder load rating. Okay, it has been performed. So let's take a look. Excel report. Okay, this is a load rating. Okay. Okay, so this is an example of load rating report. In our simplified model, I considered only HL93 truck. So here we can see load rating for HL93, which is this for based on moment. For if I have one load rating report for complete model, which is basically the same. Load rating report. Okay, so this is if we run our model and perform load rating, we come up with this load rating report summary. Here we can see all the rating load combination that we have defined and load rating for each conditions. It also provides, so in this case, critical location is element 39I. So we have a detail. We also have a detail report for that. In detail report, MIDAS provides, in detail report, we can see a capacity calculation, then dead load demand, live load demand, and rating factor calculation. So currently MIDAS Civil has capability to come up with a load rating number for only composite girders, a composite section. It doesn't have any feature that will allow us to do load rating of cross-member members and in diaphragms. in diaphragms, but we can actually come up with required values to perform load rating of crossmember members. For example, in this still designed code, to perform to do a still design, we have to first select a still code. In our case, it is LRFT 2012, and next step will be selecting a strain reduction factor from code. Once we fill this, next step will be modifying material property. So if we have to modify anything, we can do it here. These two are the still material that we previously defined. Then after that, we can go to code check, and MIDAS will perform code check for all the still elements. It also has MIDAS also provides a graphic summary report for still code checks. For example, I will take one external diagonal bracing. This is a graphical report that MIDAS generates. Here we can see like it did all the necessary code checks, and it also have member force information, member properties, and we can also generate a detailed report here for our still members. This is an example of detailed report where we can see member forces, and it does all the necessary code checks for us. At this stage, from this report, we can actually get force acting on a member on each crossmember members, and it also calculates the capacity of member depending upon whether it's compressed or in tension. So we can use these two values, the capacity calculation from detailed report and force acting on those crossmember members, and we can, based upon those two values, we can actually calculate rating factor for crossmember members. Okay. So this feature is very useful if we are interested to do load rating for still members, crossmember members. So next stage is composite design. If we want to check, if we want to code check composite bridge element, for example, in this case, composite steel top girder, if we want to code check, we have to use this feature. In this section, first we select a code, then we have some resistance factors that we can modify as per our need. That's been according to our code requirement. Since our bridge has two girders, so we'll choose multiple box girder section here. The next step will be next section is composite material section. It's very similar as in load rating case. So this is a SRC material, and we can change material property from here. Similarly, we have to provide load combinations. Since we can use load combination from here. If we design this, okay. So this is previous. So once we provide necessary information for composite design, as I shown before, MIDAS will actually auto-generate a very good report, in which as we can see here, provides MIDAS will actually generates design report, where we can see all the necessary code checks has been done here. So this feature is very useful if we are interested to design check our composite girder. This is our composite girder. Okay. So this section is also done. So at this stage, we already talked about the load rating. We talked about the rating steps. Since we have lots of stuff to talk, so and time is very limited, so I'm going too fast. I can understand, but as we have seen here, there are steps which are really easy to follow, and MIDAS can perform rating design and can also produce excellent Excel reports for both rating and composite design check. We can use still design menu for code check of still members. This feature is very useful if you want to do load rating of cross-spam members. Now I will talk about how I did load rating of in-diaphragm. For in-diaphragm, MIDAS doesn't have a specific capability that gives you a load rating number for in-diaphragm. So in our model, in our project, we use stress evaluation from MIDAS Civil, and we use that information to calculate our load rating for in-diaphragm. So let's go to in-diaphragm. Let me activate in-diaphragm first. Okay. So this is our model. And we have option, which is plain stress and plain stress option. So we can choose any load combination from here. So for example, I'm choosing SL93 load combination. This sigma effective is bone mass stress. We can also say it as effective stress. So in our load rating of in-diaphragm, we used bone mass stress to calculate our load rating. So we can actually, for different load combinations, we can come up with stress value for in-diaphragm, and we can later use this value for load rating. Because our capacity of plate is around 50 kips KSI, and we after that we can, for different load cases, we can come up with stress in plate elements. So using these values, we can calculate load rating of in-diaphragm. Let's show you one example. So this is stress distribution in diaphragm. We can also see stress distribution based on construction stages. For construction stage 1, where we activated only steel elements, our stress distribution looks something like this. We can also have legends. So yeah, so basically MIDAS actually allows us to model in a composite girders. They recently, in 2015 version of MIDAS, they actually included this feature where we can model steel tub girders, and currently MIDAS has the ability to load rate composite girders, but for load rating of cross-frame members or in diaphragm, actually they have sufficient information here, so we can use that information to load rate other elements. So with this, I want to thank everybody for attending today's webinar, and thank you very much.